Block 2 stuff. Let's see, I always start with something, you know. I was at Walmart yesterday. The funniest thing, I guess it's not really funny, but I get out of my truck and it's like a, I don't know, maybe 20-degree uphill as you're walking into this Walmart. And I'm walking and I see, I know, thank you. You say, how do I get up that incline?
How do the people?
Oh, I know. Well, I had to give you the incline because it's just enough to make like carts roll. You've seen a random cart roll before, you know, that's no big deal. But this is completely different. Because I get out and I start walking and there's a lady driving up, so I kind of go to the side. But in front of me, about 20 feet up, is a guy with one of those, he works there. He has that thing that pushes all the carts. And he has like 3 sets of carts that are stacked like 2, 3 deep. And as I walk up, he's getting one and he puts it on the front of that thing and just starts walking up that hill. And the other 2 just start rolling down the hill towards this lady's car. And they're going both directions. And I'm like, do I save her car? Do I save that car? And so all of a sudden, in my relaxed mode, I'm scrambling. I got both of them. I ran over, grabbed that one, threw it over, grabbed that one. And then the dude just kept going. And there's another guy in the front yelling at him, "You gotta get the carts when they're rolling off." And the guy, he just ignored it the whole time. The guy in this phone. Anyway, save that lady's car and somebody else's. Yeah, it was. I wasn't saying it to brag. I was all of a sudden I go from relaxed to stressed. Like, why is it my job to save their car? We're gonna hit mine. I was further in than the car was about to hit. So I just completely ignored them. Like, I got all I'm taking. He left. And I just started rolling. It's a little harder because they don't turn as easier when there's 2 or more on it. I figured that out yesterday. Oh, fun things in life. We gotta get started though, so we can get through this today. What else? I can talk about my pains of putting my suspension back together. Anyway, good problems to have, like I said yesterday. Okay, overview. We stopped here. I wanted to go back to this chart, like I said I would. This is described. Really, what we're starting to look at is the voltage gated channel. Right? There's a big difference between leakage channels, lighting gated channels. They're all required, they all exist, but they're activated at different times. Remember way back in the beginning of this, I said, hey, sodium, other molecules are able to get in and out of a cell many different ways. So you have your leakage channels here that we discussed, and then you have the lining gated channels. Right? Some stimulus comes along and activates a lining gated channel. We say some stimulus, but what we've generally been referring to is, as an example, is an acetylcholine molecule comes along, activates a receptor on another end plate. That's a stimulus. Chemical stimulus that opens that lining gate. Sodium comes in. So we're to the point now to say, okay, well, what does that cause? Or what can it cause? If sodium starts coming into a cell, right, it can cause it to depolarize. So it's already polarized. If we can depolarize it enough, right, and 2 of y'all told me yesterday, yeah, we kind of all are getting this because we see it in multiple classes. You can depolarize it enough to get to -55, I always go boom, right? The action potential takes off. You've depolarized the membrane. If you don't get to 55, nothing's going to happen. I'll explain to you what that's called a subthreshold stimulus, and I'll explain to you in a second what that means. So this chart's referencing mainly what I want to talk about is the sodium channels, voltage-gated sodium channels. So when you have the stimulus, I said all that so I could go back and say, well, the stimulus, I asked yesterday, y'all answered, what's the stimulus? Something that activates a lighting gate, or maybe a mechanical gate, something that opens a gate that allows sodium to start coming in a little bit more. Once it reaches threshold, that would be here, -55, that's a key point. At that exact point, the voltage-gated sodium channels will open. And what this green is showing as it goes up, this is representing sodium flowing into the cell, the depolarizing phase. And then you're going to find, once you get up here, your sodium gates close, or closing, and then your potassium gates open. Now somebody asked about numbers yesterday. I don't care about what voltage your potassium gates are open. I only want to look at sodium. But for the graph purposes, that's when your potassium gates are going to open, and that's called the repolarizing phase. Potassium gates often stay open, in layman's terms, a little bit too long, and so it kind of hyperpolarizes it, but then it will balance back out to resting membrane potential. Right, so you can read through over here and talk through all of that, what's actually going on. But that's the basics of it. And like I said, the key point for me is knowing when voltage gate and sodium channels open. So this is just a recap of that, kind of showing you. I'm not going to walk through all this again. I put this here for a little further explanation if you want to read through it, but it's taking the info that's there on the right and kind of just restating it and showing you the actual gates there. It's not something that you're going to need to label or anything. It's just there for enhancement of knowledge there. Some people like more of a visual than just a graph. All right. Calcium. We regulate calcium homeostasis in the body, and what they found is calcium molecules actually bind to like sodium voltage gated channels. So if you have low calcium levels, that's going to affect this because calcium ions are positive, right? Sodium ions are positive. The voltage gates, if they have these calcium ions attached to them, then that will increase the voltage level required to open the gate. But absent the calcium molecule being there, the gate will open much sooner, easier. I'm going to talk numbers in a second. So you have calcium that's in the extracellular fluid. It has an effect on the sodium voltage gates because it's binded to that. And all of this, we can drive this down, and let's just walk through it without reading through all the words, is if threshold is negative 55, that threshold at negative 55 includes the fact that calcium is already bound to the voltage gate. So let's use numbers, just make them up. But absent calcium attached to the voltage sodium gates, let's say now that gate would open at negative 50. Sorry, that didn't work. Negative 60, right? So now if you have a stimulus that comes along, when you reach negative 60, because there's no calcium bound to it, you would open that gate, rather than it having to go all the way depolarized to negative 55. Right? So if you put calcium there, that would work. What that's going to cause is if you have a low, like extracellular or systemic calcium, your nerves are going to get excitable, like restless leg syndrome kind of stuff. Not exactly, but the key point there is absent sodium or absent calcium bound to the voltage gates, you're going to open at a what's the word for it? A lower threshold. So instead of negative 55, it might open at negative 65 or lower. Does that make sense? I didn't feel like it made sense when I said it, so it's one of the, I'm going through it thinking, well, I understand that, but I don't know if I relayed that well. Let me know if I did. The key here is sodium or calcium deficits lead to excitable muscles, nerves, because you've lowered the threshold if they're not there. All right. Either y'all don't care or you figured it out. Hey, propagation of nerve impulses. We're finally getting, we've referenced many times, or I have, conduction of action potential. Now I'm going to show you how that occurs. That's called propagation. So all nerve impulses, when you look at neurons, is going to start at the trigger zone. And it's going to move down through that axon. That's called propagation, and it's a positive feedback system. What that means is each segment in a basic unmyelinated neuron, each segment, one segment will depolarize, that will cause the next one to depolarize. So you can almost think about it like the depolarization of the first segment is the stimulus for the depolarization of the next segment, and so on, down to maximum. That's propagation. So as you start to depolarize each area and cause more sodium to flow in, that's going to open the voltage gates from one segment to the next. So all this is saying is, as you depolarize a segment, what you depolarized, it meant you opened the voltage sodium gates. And as one segment does that, voltage gates will open, they'll close, that will cause the next segments to open and close. And all of that's due to the fact that what are we really talking about when we say the voltage gates were activated is that they're open and the sodium's coming in. You can do this one of two ways, the way I was just describing it, segment to segment. And you may have not noticed that I threw in there at first, I said, well, we're talking about an unmyelinated axon. Right? Because myelinated axons are going to do this differently. So when you look at continuous conduction, that's step by step. One segment, like of an unmyelinated neuron, boom, 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 down the axon. Saltatory conduction is much faster and is only found in myelinated neurons. Right. Saltatory conduction is going to use the nodes of Rambier. Y'all remember those at all? The little bumps that are in between when we talked about Schwann cells myelinating axons or oligodendrocytes myelinating axons. When they're myelinated, the nodes of Rambier are in between those myelin. And the fact is, in a myelinated, or let's start with this, in an unmyelinated axon, you used to have voltage gates all the way down the axon. In a myelinated axon, all of the sodium voltage gates are concentrated at the nodes of Rambier. And so if you have, well, let's just switch and I'll show you on here. This is saltatory and continuous conduction. Here's continuous on this side. And so we're going to open voltage gates here, which will cause it to open here, and here, and all the way down. It'll open one segment at a time. That's continuous conduction. But if you have myelin, in the red little circles here are Schwann cells, or just a myelin circle. So in between each one of these, we're going to have nodes of Rambier. In those nodes of Rambier are where the voltage gates for sodium are located now. They're concentrated there. So when you depolarize this area here, it's going to essentially jump myelin. Okay. Now you'll notice if you look at just this one here, see the little dotted lines? I'm not going to really get deep into that, but what that is there is a flow of ions that kind of circle around the membrane there. That's very, very, very basic way to say that. But the key is whatever this is a movement of ions. But I just want you to think of it as there are voltage gates here, and they have the ability to use myelin to quickly go from here to here to here. Boom, boom, much faster. I don't care if you understand the ions flow there, just that the voltage gates are in the nodes. That is much faster and it requires less ATP. The body likes to use that. Don't ask me why all neurons, someone's getting to it in their head, I'm beating you to it. Don't ask me why why aren't all axons myelinated? Well, the simple answer actually is when you look at certain areas, you need delayed times sometimes for action potentials to get there. There are reasons why you would want to have an unmyelinated axon versus a myelinated one for how fast the adjustment or action occurs. We're just not getting into that deep into the physiology. For now, we're just going to notice that, hey, some axons are myelinated, some aren't. That'll make a whole lot more sense when we get to the sympathetic, parasympathetic systems and looking at their myelinated versus unmyelinated axons and how they affect us during fight or flight. Okay, when we look at metabolism, we're still talking about neurons, so metabolism in neurons is really dependent upon glucose, right? Aerobic metabolism of glucose. So that's going to require large amounts of oxygen. That's why when you look at the brain, we consume about 20% of the glucose, even sitting at rest, is going to your brain. You must have an uninterrupted supply of oxygen and glucose to sustain the electrical activity. That's why if you choke somebody out, they're going to go out pretty quick because you've interrupted that flow versus like cutting off the blood supply to your arm. Another way that we can talk about the speed of axons is how large they are, or whether they're mounted. So if you look at power lines outside, most people would understand. If I have a power line the size of my finger that's 20 feet long, running the same voltage, doesn't matter. But I have a power line that's the size of my forearm, running the same distance, same voltage. The one that's the size of your forearm will conduct that much quicker. So the larger that fiber is. Same thing occurs with axons. Okay? And we break them down and say, well, there's A fibers, B fibers, C fibers. A is fastest, B is fast, C is slow. Right? From now on, everywhere you go and you hear about axons and speed, just remember that A, B, C in that order. Fast, or let's go. C is slower, B is fast, A is the fastest. A and B are going to be myelinated, C is going to be unmyelinated. That's it. It doesn't matter to me how fast they're traveling, just recognizing that fact. So when somebody tells you, and you're studying like a neuron, they say these are type A fibers, you would know automatically, well, that's myelinated, and because of that, it's fast. If they say B, you're like, yeah, that's myelinated, but it's just not as fast as A. When they look at these speeds. And there's a lot of studying in this, right? You've heard of people saying that they have more A fibers than other people, and that's why they're such great athletes. Have you heard that? I don't buy that. I don't know. Just what's the easy way?
A fibers are already there. B fibers will be there soon, and C fibers will see there eventually.
Yeah, I like that. Did y'all hear that? Make up your own. He said A fibers are already there, B fibers will be there soon, C fibers will see when we get there. Did I say that?
You're welcome.
Now I'm going to know those forever. Or you can just teach them to like 15, 20 classes in a row. Then you kind of get them. I'm just kidding. That was good. That was actually good. All right, perceived stimulus intensity. This is a brain interesting fact. All nerve impulses are perceived are the same size. So how do we distinguish between different stimulus? In other words, how do we distinguish between like light touch and pressure? There's two different ways. One is either the frequency of impulses, how fast are those action potentials traveling down an axon, or the number of sensory neurons that are activated. So if you look at frequency, if you have a light touch, the frequency or how fast the signals are going to get on that axon are kind of slow. They're really wide space. And if you were to press down harder, that's going to cause those action potentials to go faster down that axon. Right? We always talk about one action potential traveling, but remember we summed them up, we can send more. And so we can send multiple action potentials down an axon, and we can change how fast we do that. Whether there's 1, then 2, then 3, or whether there's 1, 2, 3 going down that axon. The faster they come, right, it starts to tell the brain that that's pressure. More intense activation of the receptor, or the fact that if you deform, you push harder down into your skin, you start to activate more sensory receptors as you do that. So the brain will pick up on that and go, okay, well that's more of a pressure touch than just a light touch. I find things that the brain sorts out like that interesting to me. How does it figure out light versus 2-point versus 1-point touch, discriminatory touch, and all that? That's where a lot of that comes into this. But that's all we're going to say about it, but it's really interesting. So we're going to go back and look at action potentials and what happens. If we've talked about how we open voltage gates, but if you're at -70 at resting membrane and a stimulus comes along and it, like a lagging gate's open, that's the stimulus, and take you from -70 to -65, but it does not reach threshold, that's called a subthreshold stimulus, and nothing will happen. You will not send an action potential because it will just go back to resting membrane potential. Okay? If you have an action potential or more than one, if you have enough stimulus come along that it hits -55, that will cause the action potential. So just like we saw when we said, well, that's the voltage gates jumping open, that's causing, that voltage gates opening causes that action potential, so you can see that go up. That's a threshold stimulus. And then you can have a super threshold stimulus to where you have several action potentials because you have such a large, you have one action potential, then you have more stimulus causes another action potential, then another, you can keep hitting threshold. If you keep hitting threshold, it's perceived as a stronger stimulus, or the difference between like light and pressure touch. That's increasing the frequency. The next 4 slides are just kind of a recap before we move into the last part of this, is when we receive stimulus, we're starting back, and you may, if you're kind of already understanding it, you're like, yeah, I really don't need these 4 slides. I agree with you. It's just kind of a recap of what we talked about, is when you look at the dendrites, they are receiving stimuli through activation of ligand gates or mechanical gates, and in sensory neurons, that produces what's called a generator or receptor potential. For now, don't worry about generator or receptor potentials. We're going to get into that in all of our neuro stuff. And in motor neurons, that either creates an excitatory or inhibitory potential, postsynaptic potential. Either excited or either inhibited. Okay? So when you look at the cell body is receiving stimuli that is either excitatory or inhibitory. Okay. Like I said, we're going to discuss this more next block because some of this goes into what we got to get to. But here's the key. If it's an excitatory stimulus, it moves you closer to threshold. If it's an inhibitory signal, it moves you further away from threshold. So an excitatory stimulus will depolarize, right? And an inhibitory will repolarize. It'll hyperpolarize. Right? But think of -55 sitting there, and the stimulus comes along, right? And it can move you closer to threshold. That's excitatory. If I go away from threshold on the graph, more negative, you're inhibitory. So different neurotransmitters cause that. I need to stop because we're not going to understand that for this test. We're going to understand it for next test. We're going to get too deep. The point here for now is you receive stimuluses that either move you closer or further away from threshold. In a multipolar neuron, remember the trigger zone's here. In pseudo-unipolar, the trigger zone, we discussed that at nauseam, is out further. Either way, wherever the trigger zone is, it's going to evaluate. Remember, I came back in and I tried to talk about chemical and voltage gates channels meeting up at the trigger zone. All of these chemical gates meet up, and they take all the EPSPs, excitatory postsynaptic potentials, and all the inhibitory postsynaptic potentials, and they basically grade them. Like, how much excitatory versus inhibitory signals am I getting? And if the ultimate result is that you reach threshold, then you will have an action potential start. Nerve impulse. And that's going to propagate down the axon. When we say propagate, that can mean continuous or saltatory. That doesn't matter. It's going to go down this axon, and it's going to be reinforcing because it's going to depolarize either each segment or from one node to the next. The amplitude will always stay the same. And it's going to go all the way down. These are terminal branchings. And it gets all the way down here to the red. The red is synaptic impulse. When you reach the synaptic impulse, that nerve impulse, this is a part where I know people get confused. So the nerve impulse that traveled and depolarized each area of this axon will go all the way down, and it will depolarize. Remember, because it's all or none. It's going all. It's never going to stop. It goes all the way down that neuron, and it will reach the synaptic impulse, and it will depolarize the membrane down there at the synaptic impulse. When it does that, that will cause voltage-gated calcium channels to open, and we'll have an inflow of calcium into the synaptic impulse. It's a key point here and in other classes, and I'll explain why, is when you bring calcium into the synaptic impulse, let me say it differently. When we're looking at a neuromuscular junction, and we had that somatic motor neuron, it had its synaptic impulse, and we had the synaptic cleft, and we had the muscle. We had to get a chemical across that, and we said that's acetylcholine. Where does acetylcholine come from? How does it get into the synaptic cleft? Exocytosis. Exocytosis of vesicles. It's inside of those synaptic impulses. So you have to release it through exocytosis into the synaptic cleft. Right, here's the key for here and when you get to other neuroplasticity stuff. Here's the trick always. Depolarization of the synaptic impulse causes the inflow of calcium. The inflow of calcium causes exocytosis of the neurotransmitter. So where they'll get you is they'll say, what causes the release of acetylcholine into the synaptic cleft? And your choices might be depolarization of the synaptic bulb, or the other, that would be your distractor, because the answer would be the influx of calcium into the synaptic impulse. Does anybody see why I'm saying that to help you out? Because if not, we think technically, and technically doesn't always work, and you say, well, technically, you never want to be saying technically after the test talking to an instructor in their office, because technically doesn't fly, right? I'm being facetious to get my point across. You just say, well, technically you had to depolarize the membrane for the calcium to flow in. Right, but you're being specific. You already know that. You've been here long enough now. We're looking at specifics. The answer would always be calcium inflow causes exocytosis of the vesicle to release the acetylcholine. Did depolarization cause the inflow of calcium? Yes. Yes. I say it because they got me at 1.2. I'm a technically person too. I'm like, well, yeah, but what was the step before that? That's one of the reasons why I ask y'all sometimes things like that, is to get you ready to think the way that the parents think, so the way that PA instructors think, is looking at very specific. What occurred right before this? Yeah, that occurred, I get it, but what was here? That's what they're asking. You always got to pay attention. Y'all already seen that, I know. 3-4 tests in, right? This week, tomorrow, is it tomorrow? Tomorrow, when you kick that test butt, that'll be what, your 4th, so you got 5th. So you've had one of each though, you'll finally have you would have seen all the instructor's first exams at least. Right? Maybe not research about, did it have an exam? So, okay. I don't pay attention to research about because it's not interesting to me. I know this, if you tell me something, I'm gonna go read as many articles as I can on it and figure out for myself if what you're saying is correct. I don't trust Wikipedia, so. Alright, that's our neuron talk. Now, last thing we're going to look at is signaling, kind of how this works with tissues. And then we really, block 3 is all of neuron. One of my favorites. Don't get worried, that's one of my favorites. I'm not going to try to make you a neurologist. I'm not a neurologist. I only know enough to hurt people. No. So we already know what a synapse is, but we're talking signaling. So we need to talk about what do we mean by the synapse. You've probably already seen some of this in other classes, and that's fine. I'm still going to go through it. It's the junction between two neurons, a neuron and a muscle, a gland, whatever that might be. And synapses provide or help with homeostasis because they're evaluating and integrating stimuli, whether or not we send that chemical across that synaptic cleft. Right? If you put drugs, whatever it might be in the body, and just in general, synapses can be physically changed with repeated use. Not only that, when we get into neuro, we'll talk about, yeah, you're not growing new neurons, but as you're sitting here, even today, starting to learn, everything you do in life, you're building new synaptic connections. So neurons that may have never been associated together can create new synaptic connections. And I'll talk about that in neuro, but I think that's very interesting. Like now I created a synaptic connection that I know that if you try to take 3 carts that are connected and just whip them around, it makes you look like you're weak. It didn't turn when I described it. I made a synaptic connection. If you don't believe that, I don't want to get too further off of this because we're going to study it with this stuff. Like when you smell something and you have a memory, you create that synaptic connection. Right? Temporarily, short-term, long-term memory stuff, like your thing you said a second ago, some people, you can get it into long-term using that stuff. It's not long-term yet. I've already forgot it. I didn't really forget it. I'm smarter than that. Okay. Okay, so synapses can be physically changed. You ever heard of like up-regulating, down-regulating? Try not to get into that. The problem is, when you look at these, it becomes interesting because when you look at addiction, and you look at methamphetamines, you look at nicotine, right, caffeine, all of these activate the same receptors you already have. You're just stimulating them from an exogenous source. You know what exogenous means? It means from outside of the body. Endogenous would be you have it in you or you make it in you. Exogenous you have to take in. So your meth is exogenous, but it can activate receptors, or it wouldn't work. And not y'all's meth. I meant society's meth. Addictive stuff. Fentanyl just plain out kills you. I mean, anyway. Anybody ever dealt with fentanyl? That's terrible stuff. I'm not talking about the news. I mean, I am a little bit because fentanyl's nothing new about fentanyl other than people are sneaking it into that stuff. People don't know they're taking it. It doesn't take much fentanyl to take you out. That's unfortunate though that we're going through that. Hopefully people will get smart. I don't know. Don't take things off the street. Alright, I gotta stay on the topic. Presynaptic neuron, postsynaptic neuron. Are those words new to you or you heard them in other classes? Maybe new because they focus on the synaptic cleft, right? But if you have a synaptic cleft between 2 neurons, you're going to have a presynaptic neuron and a postsynaptic neuron. One before the cleft, one after the cleft. The one before the cleft is called the presynaptic neuron, and when we look at that, it's going to be the sending neuron. When you look at the postsynaptic neuron, that's the receiving neuron. But most neurons function as both. So what do we mean? I don't have any pictures for this, but let's draw a neuron here. Two dendrites out there. There's a neuron. Here is, I'll put a square for, that's the synaptic cleft between that one and the next neuron. So this is the presynaptic neuron, and this is the post. Neurons are hardly ever in a single series. There's hardly a neuron tract, anything, pathways, that there's only one or two, or sorry, where there's two neurons, motor neurons and stuff. So you'll have a pre and a post, but if you had, which is the case most of the time, you have a neuron here, it goes here, now you have another synaptic cleft, and this is the pre. So the signal is going to go from this neuron to that one. So it's the sending neuron. But now this receiving neuron becomes the postsynaptic. Sorry, it's hard to write. And then it will be the presynaptic to this synapse. All you're looking at is what neurons are on what side of the cleft. So it can be pre or post, depending on how the pathway is set up. When you looked at the heart had electrical synapses. In order to say it's an electrical synapse, it means that those cells on each side are in contact. Having a gap junction between cells, they're still in contact. So that is an electrical synapse, and that allows it to move from one cell to the other. There's no, I like to think of it this way, in an electrical synapse, there's no extracellular fluid or interstitial fluid between those. Because you may not realize it yet, but when you have a synaptic cleft and you have a neuron here and a neuron here, and there's a synaptic cleft in between, that's filled with extracellular fluid is within the synaptic cleft. Because those cells are not physically in contact with each other. But if you have a gap junction, connecting them, it can flow to one to the other without going outside of the cell. That's why it's much faster. It doesn't have to go through any membranes. It just goes through the junction. So if you have two that are separated, though, at a synaptic cleft, that is a chemical synapse. So in that case, the chemical is going to have to cross the synaptic cleft. Really what we're doing is we're taking an electrical potential in a neuron, changing it to a chemical stimulus to cross the synaptic cleft to create an electrical potential in the next neuron. So it's going to be much slower because of that step. And we can go back and say, well, why? Why would we do that? Why not just have the neuron connect to the neuron? Because then we haven't started studying and we don't understand receptors and the way the body uses receptors to change things, to activate things. The same way drugs. This is, if you don't find this interesting, that's fine, but here's the key. This is how we understand pharmacy. Because all of pharmacy works at these receptors. I'm trying to link it in your brain to things you already know. Everybody in here has heard of beta blockers. Well, what are beta? What do they mean by that? Beta receptors. You have beta receptors responsible for heart rate contractility in the body. The body can activate more or less of those to increase or decrease heart rate. So it can make changes. It can work with homeostasis to keep you healthy. But what if the blood pressure is too high? I can go in there and give you a beta blocker. I can block some of those receptors so they can't be activated. That's the basic example, because we've all heard of that one, but that's the basis of pharmacy. I mean, That's your mechanism of action, is where they all come from. What receptors can we block? Right. So I only gave electrical potentials one slide, and I kind of already talked about this just standing out there. Ion flows from one cell to the other. It's much faster than a chemical synapse. There's nothing new here if you understand what I just said. In the heart, we know it can synchronize contractions of muscles. So visceral and heart muscle, the only places you really see these gap junctions. Now, you're not going to see gap junctions in a skeletal muscle. It just doesn't occur that way. Chemical synapses, we have to spend more time on them. One of the things about chemical synapses, we said they can go from, there's a synaptic cleft between a muscle, a gland, another nerve. If it's dealing with one nerve to the next, they actually don't always connect to the same spot, like we visualized previously. It can be axodendritic, meaning we can have an axon that goes to a dendrite. That's the way we've been looking at them, right? Sometimes, and we're not going to talk about where the sometimes are, it can go axosomatic. Soma means cell body. So sometimes an axon from another neuron can actually synapse with the cell body. Or axoaxonic, where a dendrite synapses directly with another. An axon synapses with another axon. Don't get tied up into that. We're not going to look at that. We're going to keep visualizing them as axodendritic. One axon to the next dendrite, unless we're going to a muscle or a gland. We're not going to talk any more about somatic or axoaxonic. I feel like by now that we all understand this, but still got to cover it. But it's a good, I like big, basic pictures sometimes because it shows you what we were saying just a second ago. The nerve impulse arrives at the synaptic end bulb and depolarizes it. That opens voltage-gated calcium channels. Calcium flows in there and will cause the release of the neurotransmitter. And that will cross. So in this case, this neurotransmitter we're going to say is acetylcholine. Two molecules of acetylcholine will bind with that receptor, open sodium channels, and allow sodium to kind of come into that cell. I walked all through it, but I left this in here so that when you, what's all those marks? When you get to your study time for me, when I become important, then you'll have the words here. How about that? I'm going to erase these off. Made it look funny. Nothing new here. I just said it twice. These are just like for later. You got to understand the events at a chemical synapse. We're here in multiple classes, so we didn't get to this part again. Saying once a neurotransmitter binds those receptors, it will open those on the postsynaptic membrane. The postsynaptic membrane, if you haven't noticed, has a couple of different names. Right? We've looked at it and said, well, that's the membrane of the next neuron. In muscles, we're talking neurons here, but when you look at a neuron that's going up to a muscle, a neuromuscular junction, the postsynaptic membrane would have been on that muscle. But in that case, you remember what we called it? The motor end plate. Well, this is still motor end plate. Motor end plate is the receiving side of the synaptic cleft, or onto a muscle. Wherever has the receptors, that's the motor end plate, basically. So you have all those ligand-gated channels that are now starting to open. If enough of those open and allow enough sodium to come in, we will reach threshold and we will open the voltage gates. Will flood in, and that will trigger motor and nerve impulses. So that's a good walkthrough of kind of the last 40 minutes that we've been talking about. I'm going too fast here. I don't feel like it. So we mentioned earlier EPSP. if you depolarize the postsynaptic membrane using an excitatory postsynaptic potential, EPSP, it brings it closer to threshold. Neurotransmitters that hyperpolarize it are inhibiting, so it takes it further away from threshold. Where we see these is ligand-gated, right, positive ions, cation channels. Generally, we talk most about sodium, but we can include calcium and potassium there. So if you look at a single excitatory postsynaptic potential, generally that will not initiate an action potential. Another way to say that is the opening. Let's look at a axon to a muscle. We want to depolarize the membrane of the muscle cells, right? Well, one sodium ligand gate opening upon that postsynaptic membrane opening generally does not make you reach threshold. Can it? Yes. Does it? Not always. It generally takes more than one of those openings. Right? So a single EPSP doesn't normally initiate a nerve impulse, but the nerve is now more excitable. What this is saying is if you're at -70 resting membrane, remember the subthreshold stimulus? That's what we're looking at. Is if you're at -70 and then an excitatory postsynaptic potential comes along that depolarizes you to -60, did you reach threshold? No, you didn't reach -55. But you are more excitable because if another excitatory postsynaptic potential comes along and takes you from -60 to -55, that was it didn't have to do much, right? It's easier to hit threshold once you have more than one. It sums them up, right? But while it's summing them up, there are also inhibitory signals. So things like chloride, potassium gets thrown onto both. There's some more explanation there that we would need. But if you use an IPSP, you're going to take it further away from threshold. Let's see if I left this picture. Yeah, we'll get to how I'm going to explain in a second I'm going to answer the question in a second that nobody's asked of why do we need to have, if we need to cause an action, why do we need inhibitory ones? And I'm going to show you how that works together, how we figure that out. First, we're going to talk about, okay, now we've dumped neurotransmitter. A little bit of a switch there in your minds, right? We'll get back to it. We've got the neurotransmitter in the synaptic cleft. If you left acetylcholine in the synaptic cleft, that's not going to be a good thing. You're going to continually activate receptors. So the acetylcholine that we put into the synaptic membrane, synaptic cleft, has to be removed. It can't stay in there. It will continue to activate if so. So we got to figure out how we get it out of there. The first way that we can remove a neurotransmitter from the synaptic cleft is receptor binding. When you make your list, people often forget about receptor binding. Why? Because that's what's supposed to happen, right? Receptor binding is exactly what we've been talking about. Acetylcholine, when in the synaptic cleft, it binded to the receptor to open the gate. That's normal. That's what normally, or that's what's supposed to be going on, and it does go on. But there's still going to be some acetylcholine that's left there that didn't activate receptors. So how do we get rid of that? Well, it can diffuse. This is the whole reason I mentioned earlier again. What's between the neuron and the muscle, the synaptic cleft? What's in it? Interstitial fluid. So it can diffuse out into the interstitial fluid. So that would get rid of it. There's also acetylcholine esterase at the synaptic cleft. It breaks acetylcholine down to choline and acetyl. I don't know why I said that backwards, but it breaks it down. So acetylcholine esterase can rapidly break down acetylcholine. And the other way is uptake by cells. Under uptake, it has two different ones. They're considered, there's only, like if you're asked, there's 4 ways to remove neurotransmitter from synaptic cleft. Receptor binding, diffusion, enzymatic degradation. The last one is called uptake by cells, and it's splitting the difference here and saying if the same cell or neuron that released it takes it back up, that's reuptake. I took it back. If other neurons can still pick it up, that's called uptake. It's uptake because they didn't release it. You know what I mean? Alright, so we'll have to take a break there and talk about, then we'll look at summation. I think this last part will tie some of that together for you. Let's take a break. That was a good hour and enough digressions. The funny thing is, as much as some people complain about my digressions, I use them like I should have been digressing, because about 10 minutes ago I could see I lost about half a question. That's when you digress. I'm fine. Well, I made, man. Look, I did good. I'm only going 2 89. We will fix it.
IL-1 first acid. Get the TNF alpha.
Right.
Doesn't have a lot of things from that.
Yeah.
Inside.
Even if you do it for more than if you do it for more than 3 days in a row, you're becoming used to it. And you're gonna rebound. But I found an alternative. Here's the alternative. If you have time, forget it. You're gonna get it's called Sinus Buster, and they have it straight for me all day long. No rebound, but it's capsaicin. So I'm like, oh my god, it'll burn the top of your head when it's raining. It'll clear you out. And they have the capsaicin spray. It's 100%. Won't change anything. It's kind of fun to watch somebody. Once you do it a few times, you know what's coming. The first time they do it, take that on long drive.
I have been type 1. The reactive have to say 5 times. Red berets can and then green berets are green berets are typically separated like 2 MOS, you have like 2 other tribes. IL-12 activates that.
does amazing tests. So it does.
Oh yeah. Just Esquivel past the primary.
The gamma these are like incredible hole. It's fucking everything.
Primary.
When you're turning into the hole. Just strength and numbers. Gamma ray hole.
Oh yeah.
I don't have one for IL-6 yet. Two-phase protein synthesis by side factors.
That one is not like that. It's sort of recognition. Because like in your review,
I'll show you. Yeah, I barely. Discord.
yeah. That's why it's in place. Well,
I was
That's what I've learned. My wife got some. She can't manage like any days. She's standing like all right, y'all ready? We can finish this now. All right. So most people have a lot of neurons. I say most, we can't include all. It wasn't faith in some of our people. That nobody in this room, but so we've been looking at neurons and can't say that. I was thinking of somebody else. Sorry. You're looking at neurons, and I will say, you ever look at it, and this is very negative for me, but people look at me sometimes too. Everybody's somebody else's idiot. You know, and I realize that. I'm somebody's idiot too, and that's fine. But I looked at this, after the car incident, I was leaving Walmart, and I was pulling off in my truck. And you ever look at like a family, a mom and two kids, they had two kids, they're probably 19, 20 years old in the mom. And what caught me off guard is they all had on black t-shirts with some weird saying on it. So it just stood out for a second. And then I looked at their face, and this is the negative part. And to me, just looking at them, none of them looked very intelligent. But they had the same look. And it just caught me as I drove by and I went. But when I was said that not everybody has the same amount of neurons, they came to my mind. Now, I could have stopped and I probably could have asked them a quantum fit. This is, I'm a humble person, so I go, sometimes you stop and ask them, hey, what do you do? I'm a quantum physicist. You know, I'm betting they weren't, but. And I shouldn't be negative about people like that, but the truth be told, remember that people's opinion of you is none of your business. People have the same opinion of me. You're an idiot. All right. Good. Doesn't change my life plan. All right, here we go. Should have said that before. The last 10, 15 minutes, y'all were. I was like, I need to digress. I need to keep going. We got to get this done. My digressions serve to wake you up sometimes. Okay. Central nervous system, though. Remember, we've been looking at just one neuron. And then we got wild and we threw maybe more than one neuron on there. But truth be told, when you look at any central nervous system neuron, it generally has, we don't need to know the numbers, 1,000 to 10,000 synapses talking to it. So we're going to look at like 5 presynaptics talking to 1 postsynaptic, but that's just to simplify it so we can learn it. There are thousands upon thousands of neurons talking to neurons talking to neurons, and each one of them is arriving at the synaptic cleft. And so synaptic, the info that goes to synaptic cleft has to be integrated, evaluated, and that all occurs generally at the trigger zone. Right? So the trigger zone is like the command center. It's going to decide. It'd be like if I was the trigger zone and I'm a neuron, but I'm a neuron and I'm the one that has the trigger zone that's going to send a signal. And y'all were all presynaptic neurons talking to me, and if I said, I'm going to send the decision, now I need to know whether or not I should send that decision and what it should be. And excitatory would be, yes, we're going to move the test. Inhibitory would be, no, we're not going to move the test. And if I ask the room, hey, do you want to move the test tomorrow to Monday? I would get a lot of excitatory and a lot of inhibitory. And on a bottom level way of thinking of it, I would just sum them up and say, okay, we got 67 people, 40 people were excited about it, right? I lost my numbers. 27 were inhibited about it. What's my signal going to be? We're moving the test, right? We're excited about it. That's something you should never do in an iPad classroom, is ask them anything about the schedule and whether we should move it. You just move it, all right? Because you can't get people to agree on it. Because I'll tell you, I'm the opposite. Once they published the schedule when I was here, now that I work here, I'm moving around a lot too. When they would publish the schedule and post the test dates, I put them up. I did not want anything ever changed. Because I'm set, that's what I'm going to do then. I got a game plan in mind. And they want to move on. I'm like, why? I don't want to worry about it all weekend. Let's take it Friday. But there's plenty of people with an opposite view of mine, for sure. That's why I say it sometimes pays to dictate from being in the class in defense of you. Okay, so the greater EPSPs, the more likely it is that you will reach threshold. We're going to look at how neurotransmitters are dumped into synaptic cleft. That's called summation. Right? We're looking at things like spatial summation, temporal summation. Spatial summation means that you have neurotransmitter that was released by many different presynaptic neurons. Right? Temporal summation is when one neuron releases neurotransmitter rapidly. One after the other. It's easier with a picture. So in this would be called spatial summation, where you have more than one neuron talking to the postsynaptic neuron. And so each one of them is releasing neurotransmitter. There'd be many. And then you can also have it where you have a presynaptic talking to a postsynaptic, and it just jumps a mass amount one after the other, acetylcholine or whatever it might be, out into the synaptic cleft. That would be called temporal summation. Still going to sum up. Sum up how many excitatory gates to be open, that kind of thing. So once again, if the total excitatory is greater than the inhibitory, we're more likely to reach threshold. But if we don't, doesn't matter how many excitatory postsynaptic tensions you have. It's not really taking a vote like I did, right? Because my analogy doesn't work here, because no matter how many excitatory postsynaptic potentials you have, you still have to have enough to reach threshold. So if you don't, that's your subthreshold stimulus, and we know that if you're at a subthreshold stimulus, it's easier to get the threshold if another stimulus comes along. Okay? So if those total excitatory are greater than the inhibitory, in general, you probably will reach threshold and generate one or more nerve impulses. If its total inhibitory is greater than the excitatory, I hope this makes sense already, you're probably not going to reach threshold. It's going to inhibit you from reaching threshold. So a basic way to draw this out is to say, okay, well, here's summation. Now, in this picture, we have 5 presynaptic neurons. Each one of these, if you look closely, this is telling you that this neuron is causing excitatory postsynaptic potential. This neuron is also causing excitatory postsynaptic potential. This one is also. So 1, 3, and 5 are releasing a neurotransmitter and causing an excitatory postsynaptic potential. 2 and 4 are causing inhibitory postsynaptic potentials. So in that case, if all of these are generating their neurotransmitter at the same time, are you more or less likely to reach threshold? You're more likely to reach threshold. Because the last slide was saying, this doesn't mean that you did, but you're more likely to, because you have more excitatory. That's where we're going to leave it for now. We're going to look at kind of the last part here is neurotransmitters. And I want you to, well, now that we're awake a little bit, I want you to hear me closely, is we're going to talk about neurotransmitters, and we can talk about neurotransmitters forever. Right? You're going to hear about them in a lot of different classes. What I'm trying to get across to you here is I want you to learn the neurotransmitter classifications. I don't want you to worry yet, as we're going through these next slides, of going, okay, what does each one of these do? How are they made? All that stuff. What I want you to do is be able to recognize the categories and subcategories that they fall under. You'll see what I mean. So there are lots and lots of neurotransmitters or chemicals in the body that they suspect to be neurotransmitters. And neurotransmitters sometimes are also hormones. So endocrine glands, there's neurosecretory cells that are in certain areas of the brain. And so we find that a lot of things in the body can be a neurotransmitter, acetylcholine being the most popular one there. But like I said, there are some hormones that it gets confusing because when you look at things like renin, you say, well, is renin an enzyme or a hormone? Or is it a neurotransmitter? A lot of things depend on where it's being used at. You'll get into that in a minute. Okay, so neurotransmitters, the way we're going to break them down are based on size. And you either have small molecule neurotransmitters or what's called neuropeptides. So those are our 2 big categories. Like if we wrote on each whiteboard, I should do it that way, but it takes so much time around here. We need the smart boards. I'm going to put that on my Doge email. We got, we don't want to have to do the 5 things I did last week. I never did get to I wrote these 5 things out on my 5 things I did. I didn't know if it'd do well for job preservation when AI took over and read through all my responses. But if you separate, and I put small molecule neurotransmitters and we classify them over here, and then I have my neuropeptides over there. That's the 2 large. We have neurotransmitters, small molecule neuropeptides. That's how we break them down first. The small molecule neuropeptides are where we find acetylcholine, amino acids, the very important biogenic amines, your ATP and purines, nitric oxide. All of these are considered small molecule neurotransmitters. Most of these, when we look at things like acetylcholine, it's going to have an interesting fact to it that we're not going to fully understand until next block, but I'm going to mention it like I do with a lot of stuff. I know it drives some people crazy that I preface stuff before we get there, but the way I like to do it. So acetylcholine is released by a lot of peripheral nervous system neurons. Well, we can generalize that and say if you think about every skeletal muscle in the body uses acetylcholine as its neurotransmitter to activate it. So in the PNS, there is some in the CNS that uses acetylcholine, but most of it we talk about is peripheral nervous system. So here's the new thing. Acetylcholine, we keep saying, activates receptors. Now, then we brought in, well, acetylcholine does that, other neurotransmitters, and then we said, well, some neurotransmitters, or some transmitters can cause excitatory potentials, some can cause inhibitory. Well, acetylcholine can be excitatory or inhibitory. How the hell does that, I was trying to speak like you're thinking in your mind. You're like, what? How the hell does that work? How do we know the difference? Isn't acetylcholine just acetylcholine? So if acetylcholine is the same molecule no matter where it's in the body, how in the world can it be excitatory and inhibitory? What do you think? We're going to talk about it in the next block. But what do you think would be the difference in whether it's excitatory or inhibitory? That's partially true. I mean, I agree with you. That wasn't what I was leading towards, but that is going to come up next block, right? What you're saying. Yeah, and what you're saying ties into what you just said is, I was trying to keep it more basic before we get there, is when you look at acetylcholine and it gets dumped into a synaptic cleft, whether it's going to be excitatory or inhibitory is going to depend upon what receptor type is there. Because what we're going to learn next block is we have different types of acetylcholine receptors. And when you activate one type of acetylcholine receptor, it causes excitation. When you activate a different type, it causes inhibition. So, yeah. I gotta say other stuff. Yeah. So you're all right. I mean, I just didn't want to get too much into it, but that's why. And actually, even further than that, like you talk about that, is not only the receptor, but what type of cell is it talking to also matters. But for now, it can be excitatory or inhibitory. I'm not going to give you any more than that. When you look at amino acids, they can also be excitatory, inhibitory. Most of these neurotransmitters can. Most of it depends on the receptors. You don't really have to worry about whether it's excitatory or inhibitory at this point. But if you look at, and you've probably heard of some of these, excitatory examples are glutamate, aspartate. You look at GABA there, inhibitory, vitamin. We find most amino acids are in the central nervous system that we're using them. You can write on there that I don't care if you know the most common examples here. Remember, I'm telling you again, so you've heard it twice, I want you to classify them into what they fall under. So what's really important about amino acids is a small molecule neurotransmitter at this point. Some of them I give you a little different information. Biogenic amines. So biogenic amines are found in a lot of different foods, so they're called exogenous amines. And they have the ability to be absorbed directly into the intestines. As neurotransmitters, we generally associate them with the brain, and depending upon the receptor, once again, we keep just repeating the same thing. They can be excitatory or inhibitory. Okay. Now here's the part that I say biogenic amines are important, because if we break biogenic amines down, we're doing subcategories. I'm trying to keep those who don't track it tracking. Neurotransmitters, small molecule neurotransmitters, neuropeptides. We haven't even started talking about neuropeptides. We said, okay, well, we have amino acids, we have acetylcholine, now we have biogenic amines. Now you got to make a new subcategory and say, okay, well, you have small molecule neurotransmitters, you have biogenic amines, and then we have some that fall under the biogenic amines. That's the way I'm wanting you to start picking this up to learn. So under the biogenic amines, you have histamine, serotonin, and what's called the catecholamine neurotransmitters. So histamine, we know is part of the inflammatory response. We talk about mast cells and all that. But it's also thought to help with mediate, as they say, arousal or attention. Serotonin is thought to be involved in sensory perception, induction of sleep, right, temperature regulation. and then we get to catecholamines. So dopamine, and two that I know you've heard of, norepinephrine, epinephrine, adrenaline, noradrenaline, those are considered catecholamine neurotransmitters. Right? So that's your three different categories that fall under the biogenic amines. The reason I go through these is two things: to make you understand there's more than acetylcholine as a neurotransmitter, but also to help you classify them so that as you start learning them in other classes, you kind of know where they fall. But that'll never come back and get you like, well, you didn't know that, what type of neurotransmitter is adrenaline or epinephrine, right? Well, it's a catecholamine neurotransmitter. Well, what if somebody took it further and said, okay, well, what class do catecholamines fall in? You would have to answer the biogenic amines. That's why I'm making you just learn the basics for now. Not so much about what they're doing. That's all of our small molecules. I didn't build a slide on ATP, purines. They just follow that classification. Now we're switching and say, well, what about our neuropeptides? They're found in both CNS, PNS. They both, same as before, they can be excitatory, they can be inhibitory. I didn't mention that on the other, all these are formed, right? They form in neuron cell bodies, get released. So neuropeptides are a little different in that normally most of the neuropeptides are also serving as hormones. Hormones are going to regulate things throughout the body because they're going through the blood, right? So they can do both. And we only have one slide on neuropeptides. Because when you look at neuropeptides, where you're going to talk about this later, is certain brain receptors, or neurons, have receptors for drugs like opium, morphine, heroin. But the body already activates. Just think logically. If you take morphine, what is it doing? Well, morphine makes your brain ignore pain. The pain's still there, but it ignores it. How is it doing that? It's activating receptors. Okay, so morphine relieves pain, right? Well, if those receptors are already there, that morphine was made, it's synthetic, right? It was made to activate those receptors. That means that the body already makes, talking out my butt here as we studied it back earlier, it makes something similar to morphine that already activates those receptors, right? The body already, what I'm saying is the body already has natural painkillers. Morphine just activates those, right? It's an agonist for those. And so they're called enkephalins, endorphins, dynorphins. These are receptors are called opioid peptides. Right? The opioid peptides are thought to be the body's natural painkillers. We could go further into this and go read studies and things about why do some people, they slam their finger and they don't hurt near as bad as the next person. Some people experience pain worse than other people. I don't know whether that maybe it has something to do with their receptors for pain. We know that there are people who have no pain, right? They don't feel pain. You see, wasn't there a movie recently about that or something? What's it called? What's that?
Deadpool.
Novocaine.
Novocaine, is that it? Anyway, I need to watch that. I don't think it's a good thing. Pain is good. Pain is there to protect you. I did not think that yesterday when I sat up off my creeper and hit the rear drum in my head. But pain is a good thing. It says, stop doing what you're doing. That hurts. All right. We're switching to neural circuits. In other words, how are neuron circuits set up? Billions upon neurons, they've mapped out and said, okay, there are different types of circuit systems in the body. So what this group of neurons that process this is a specific type of information. As they map this out, they saw they're set up certain ways. Not that they fully understand this yet. So we're gonna break them down and say, well, what's a simple series of diverging or converging circuit, reverberating, or parallel after discharge? These are all ways that neurons are connected. So if you had a simple series circuit, that would mean that you have one neuron talking to another neuron. You have one presynaptic, one postsynaptic. Almost all neural circuits in the body are more complex than that. The only place I can think of that you have one neuron talking to one neuron would be a monosynaptic reflex, so one synaptic reflex, and that does occur. But most circuits have more than two neurons. A diverging circuit. Diverging is when you have one presynaptic neuron that talks to two neurons, and they talk to two neurons. You know, it's the old phone commercial they used to have. You'll probably remember they say, you know, talking about anything, it's like advertising. One person talks to two people, they talk to two people, and exponentially it diverges out, the information gets out there. Right? So you're amplifying the original signal. And sensory signals often use diverging circuits because they're related to different parts of the brain. Right? When we look at a diverging circuit, the sensory that I touch something doesn't just go to one area. Because what if what I touched activates a pain receptor or heat? It's hot. I'm touching a hot plate. If I touch a hot plate, that info from those receptors is not going to just go to one place in the brain. Because what do I need to know it's hot, but I also need to do what? Move my hand. So the sensory gets sent to many different areas. It diverges so that all those areas know that at the same time, and I can pull my hand out. Right, so that's a diverging circuit. When you look at converging, you have multiple presynaptic neurons, and they're going to talk to a single one, cause that action. This is the way motor neurons synapse with skeletal muscles. Okay? So in this case, you'll get more effective stimulation of that postsynaptic neuron. So let's reverse it and say, well, motor. In my head, I have an area, motor cortex, in my cortex, I have neurons that are associated with skeletal movements. And if I touch something hot, or let's not use hot, because that involves weight. I decide that I'm standing here talking to y'all, and I decide that I'm just going to move my arm to my other shoulder real quick. That action came from my cerebral cortex. I decided to do that. That's not an involuntary action. But if this says, if you could send an electrical potential straight from here to my bicep to make it move, would that work just by itself? No. There's info coming from other areas of the brain, specifically like the cerebellum, parts of the brainstem, coordination, right? We have to coordinate that movement, because if it was just one signal and it wasn't coming from other areas to help control the movement, I would wind up, wouldn't make it to my shoulder, I would wind up hitting myself in the face or something. It would just twitch the muscle over there. So all those areas of the brain talk to that one neuron to say, not only move, but move in this way, right? Learning through repetition, right? Practice, get in the cages. Right? Anyway, I don't know why I got to bring all those analogies in here, because we could have just said all the motor diverges to that, and cerebellum. The next two are kind of funny, or not funny, but different. The incoming impulses, you take one neuron, and it's going to provide input to this next neuron and the next neuron. At some point, this is where collateral axons come in. At some point, this axon down the line puts off a collateral to another neuron, and it sends a signal back to the beginning. Right? So it's circling back, it's reverberating and continuing, it's like reinforcing. So you can send many signals along through them, right? And that may last for hours, could last forever, they don't fully understand. But the thought is that this is what's involved in breathing, because something like breathing we do 24 hours a day, 365 days a year for the rest of our life. Breathing, so it's a reverberating circuit to cause it that we can somewhat affect. And the last one is parallel after discharge. In this case, we're going to number them. I'm going to say this is 1, this is 2, this is 3. You're going to have a couple of neurons that are close to each other. They're sending the same signal. And so the first one's going to send the signal down its neuron. And it throws off one collateral here that goes to 2, and it's going to send that signal. It also throws off another collateral here, and it's going to send a signal. This allows for very rapid activating of things. In this case, the original one sent the signal. 2 and 3 were tagged along the way to also send a signal. And so the effect is going to be that if you think about dumping neurotransmitters, you're going to have 1 reaches first, dumps neurotransmitter, immediately after that's going to be 2, 3. So it makes it a faster response. That makes sense? So it's just, it goes parallel after the discharge to allow you to effectively move neurotransmitter out quicker. Yes?
Is that something that you would see with motor unit recruitment?
Now that you can improve on this and improve motor unit recruitment, yeah. Okay, you don't talk about that one a whole lot. Generally, we talk converging, diverging, but there are instances where you may hear parallel after discharge, like that. Alright, so since neurons don't,
Question, so in all of these circuits, it's all one-way signal propagation. Is there any two-way? Are there any cases where it's two-way?
in an individual neuron, and going backwards,
Only sending it one way, a neuron?
yeah. You're always going from the receiving side to the dendrites to axon. So. See, I say things that we don't go into, and then I go, no, it's not exact. I mean, something, I debate, because I get people confused. Where's the trigger zone in the pseudo-unipolar neuron? It's out by the dendrites, right? Where's, how many connections to the cell body does a pseudo-unipolar neuron have? 1, right? It has that side one. Trigger zone's out. Y'all were seeing the picture with me, right? Actually, when you reach in a pseudo-unipolar neuron, I didn't say this before and I shouldn't say it now. Actually, they consider that whole structure going up and down. Like the cell connects and it had up and down. It showed you some dendrites and a trigger zone, and then it showed you the axon. Actually, all of that's considered an axon. But it doesn't go both ways. That's why I said actually there's some differences there. No, I've never heard of that. I'm not a neurologist, but you have dendrites that receive, and you have axons. Axons have no ability to do summation anyways, right? They can't sum up. There's no trigger zone down there. It wouldn't work. Okay, I don't know why I said all that. I just talked through 5 minutes of worthless. Not your question. My response. My response. Right, so, but the nervous system can build new connections. That's called plasticity. So individual neurons can't be replaced, but they can make new dendrites. They can make new axons, new proteins. They can change the number of synapses they make with other neurons. That's called learning. Right? It's plasticity. We create these. We were talking at the break, I think, or something, maybe during class. I said I like to do like word games, like every now and then. Like if I'm traveling, I'll buy a book of like cryptograms, that kind of stuff. That's very good as you get older, right? Because as you age, you're naturally going to have degeneration of the cerebral cortex. But we know that we have a lot more neurons than most of us use. You can create and maintain these connections to the info you used to have by challenging the brain as you get older more and more, just like you're doing here in PA school. Because it will make these new connections. But if you don't use those connections as you age, you lose them. Memories fade. Right? That's why, if they're not needed, you can also take those synaptic connections away. That's the interesting side of neuro. Alright, as we lead into the last part here, I've been saying all right a lot. I feel like I haven't very good. I always do that. I told y'all, it's on y'all. If I say a word repeatedly every day in class too much, you know, like people who always go, if there's any word that I do like and you don't tell me, suffer away. Because until you tell me, I won't know it. I don't take offense to it. You don't like to tell me during class, tell me between class. I try not to repeat words over and over, but today it seems like I've been saying, alright? Alright? That doesn't include, does that make sense? Does that make sense as a check on learning, check on looks from y'all? Okay. It went okay again. See, now I'm gonna be thinking about it. I say all that y'all need to tell me, because it drives me crazy when people do it. My buddy, when I was here in Navy, guy used to do that. He was the person. He was I would do that all day in the office. What did you say? Regeneration. We said neurons do not replace themselves. But in the peripheral nervous system, they can repair themselves to an extent with certain criteria. Central nervous system neurons do not repair themselves, not to any great extent. If you cut an axon in the central nervous system, it's not going to grow back. But in the peripheral nervous system, that ability exists. It's going to go back to involving Schwann cells. A more specific way to say it is that any neuronal axon in the peripheral nervous system that has Schwann cells has the ability to regenerate its axon. Doesn't occur in other places in the body. But here's the criteria. If it's going to regenerate, it must be located in the peripheral nervous system. It must have an intact cell body, and it must be myelinated by functional Schwann cells. If those three things are present, you can regrow and repair an axon. Generally non-existent in the central nervous system, though. So when we look at Schwann cells, and we saw they were covering here, if that axon gets injured, the Schwann cells will form what's called a regeneration tube. They will kind of connect together. And that will allow it to regrow, kind of stimulate that, and guide that axon as it regrows, if it regrows. It doesn't always happen, but if it does. And if you have people, military is more prevalent, like especially when we're in Afghanistan and stuff even more, as people get injuries and sever nerves, peripheral nerves, and they lose feeling or they lose some function, but then over time, year, 6 months, they start to rehab and grow that back. You can grow back, it just takes a long time. Right? But the key here is you can form a regeneration tube, but only if it's in the peripheral nervous system. You have an intact cell body. If the cell's dead, it's not going to be able to grow an axon, and it must be surrounded by Schwann cells. And the Schwann cells are what make the regeneration tube. The only other part there is that regeneration tube is going to ensure also that that neuron axon makes it to the exact spot that it was before. Right? Because if it didn't, if it was going to our finger, well, that's not a good example. Forget that. It's going to grow back to the same spot it was.
Bottom picture, it looks like the nose of the deer are also reformed. Do they get reformed at some point in the picture?
Yes, I mean, that's a good question, but the regeneration tube won't stay. They will go back to being sections of myelin. Schwann cells will basically separate back and they'll have nodes there again. It will be repaired. But it won't stay like the tube. You win the prize for nobody, and however long, nobody's ever asked me that. but they do. That makes it a great question. It's one of the questions. As we finish this out, demyelination. We've talked about normal, we've talked about what should happen, but what do you think would happen to a myelinated axon of the peripheral nervous system based on what I've told you, comparing it to electrical lines of base, and saying that A fibers that are myelinated are fast, and that on A fibers, not only are they faster, they have those myelin sheaths, the swan cells, and neurolemurs, but all the voltage gates are located at the nodes of Rambier, versus an unmyelinated axon where the voltage gates are all the way down it, right? So the voltage gates are at the node of Rambier. So what would happen to this conduction speed of that neuron if I remove the myelin? It would, as you start to destroy the myelin, it will slow down. But if absent the myelin on that myelinated axon, it will become non-existent. Because if you're jumping from one node to the next, I didn't explain it to you, but what did I say you're using? The myelin, there's a weird ion flow there. And to get to these voltage gates. So what's going to happen is, as it starts to deteriorate, the signal is going to have a harder time making it from one to the next. And then when it's gone, that voltage gate cannot generate a big enough potential to make it to the next one. Now you no longer have innervation. That's what demyelination causes. That's what this whole part I was referencing with here. Well, multiple sclerosis and Guillain-Barré are two examples of that. Both of them are demyelinating diseases, and they're not good to have. Both of these are technically autoimmune diseases. Multiple sclerosis is often talked about more as an autoimmune disease because you have progressive destruction of myelin in the central nervous system. Guillain-Barré involves the peripheral nervous system. So what they've seen in multiple sclerosis is the myelin sheaths start to deteriorate. Now let's stop for a second, because I just realized this, and go, well wait, you just talked about regeneration. Multiple sclerosis is a problem with neurons, myelinated neurons in the central nervous system. Do you remember oligodendrocytes are what myelinate axons in the central nervous system? But if you go back, you'll see they still have nodes of Rambier. So the same thing's going to happen if they deteriorate. I just wanted to clear that up in case you think of that later. So you get plaques or scars, and at first the signal will slow down, and then it will become non-existent, so you cannot propagate impulses down a nerve, and you'll see progressive loss of muscle function. It's a terrible disorder to have. Okay? They haven't figured that one out yet, though. Guillain-Barré is also a demyelinating disorder. I consider it still an autoimmune disorder because macrophages are the immune system, and for some reason, whether it's a viral infection, bacterial infection, it doesn't matter. Whatever reason, the immune system decides, hey, I'm going to send some macrophages to eat the myelin. It's going to strip the myelin in the peripheral nervous system from those nerves, and the same thing is going to happen. Signal will start to slow down. Guillain-Barré, you'll learn later, is not as significant as multiple sclerosis because it can vary and it can go away and things, but they're both related. Another thing that I want to mention is epilepsy. As we're talking about neurons, epilepsies, seizures are electrical activity in the brain. For whatever reason, you have all these different neurons that are sending signals without being told to do that. So if I'm just standing here and neurons in my brain, for whatever reason, start firing signals, what they call an electrical storm, it's going to cause me to have different experiences. Like it may be activating neurons that I associate with a certain smell. Right? And if you think of like migraines, some people with migraines, it triggers these neurons also. So when that storm goes off, you're just getting all these different perceptions of light and things that don't really exist, because that smell's not there. But your body remembers smells. Right? We have smells associated with memory. And so during epilepsy, you'll see that. Not all seizures from epilepsy are real dramatic. Not everybody's had a seizure, drop on the ground. There are many different types of epileptic seizures, to include one that most PA students have, absence seizures. An absence seizure is like, what's his name? Mitch McConnell, I think, had an absence seizure. Did y'all see that a couple months ago? He was on the podium talking, and then he just, they're like, oh, the aliens turned him off or something. There's all these conspiracy things. They're looking at their ears and stuff. No, it looked to me like he either had a TIA or he had an absence seizure. Absence seizure PA students have, because many of y'all become experts at this, they're sitting there looking at you, and you're talking. And I'll look at people and their eyes are locked on me, but I know they're gone. We're going to discuss under special senses that you have muscles that aren't part of your facial expression. You're going to know, I'll bring that back up. When you have absence seizure, somebody's there looking at you, they're wide awake, but they're somewhere else in their mind. Right? And I'm not talking about somewhere else studying micro. I'm saying they're just gone. What's cool about it, I've taught long enough that if you see one who continually does it, if you'll point at them while you're talking sometimes and go, so you have a degree, right? They'll nod their head, but they never really wake up out of that. It's weird. Something about instructors like me can lull you to sleep, so you're there, but you're not. Yeah.
So all seizures are part of
When you say seizure, that's what you're talking about in the body. You're talking about electrical storm, sometimes abnormal electrical activity. And there's people have seizures that you don't see all the time. But we often think of like status epilepticus, you drop down, put the thing in their mouth. It's not always like that. You're going to learn in neuro a lot of different types of, in any art, a lot of different types of seizures. Is that what you were asking? I felt like my answer made too much sense. When I feel like that, sometimes people go, yeah, I like what you said, but that didn't answer my question. All right, rabies is talked about here because rabies, the virus there, actually travels via fast-acid transport. So you get bitten by a dog or some other mediated animal that has rabies, and it's going to travel backwards in your axons. How does it do that? It's a virus, I don't know. It's a virus that can do that. But it's using fast axonal transport. Is that right, Asa?
I was curious because I did watch a video on rabies and a few people, there's only a few number of people that survive rabies. I was curious if it tries to train us to the brain and then it takes people.
But remember that fast axonal transport is using microtubules, the training system, and that's much different than saying using an action potential. So, this travels back to excitement, aggressiveness, madness, paralysis, death. Last slide, and it's very interesting if you never thought about tying this together yet, is pain. How do we relieve pain? Local anesthetics block pain from what they call somatic sensations. Touch, pain, heat, whatever it might be. They're doing anesthesia to the skin. So everybody knows you're going to anesthetize an area that you do a suture on. Well, the way this is going to work, you look at lidocaine, most common one, Novocaine. Everybody in here probably has heard of lidocaine. We inject lidocaine to do a digital block. You may never thought about this before, I'm sure, but what it does is block voltage-gated sodium channels. So you're going to be able to, that pain receptor is there. It's going to detect the pain, but it cannot send the signal to the brain because we block the voltage gates temporarily. If you can't open voltage gates, guess what you can't do? You can't create an action potential. The action potential is the nerve impulse that goes back to the brain. So that's how lidocaine works. Threw that in there. So, interesting. There are other ways and I said it earlier, and we'll get to it again later, like morphine doesn't block voltage. Morphine affects receptors in the brain, and you just decide to ignore the pain. The pain's still there. They'll give you some morphine, codeine, something. All right. That's it. That's all the info for block 2. I know. He's reminded me several times that it seems like a lot. If you're really getting tied up in an area, when you go back and you start looking at it between now and next Monday, over the weekend, please send me an email. I don't understand, I don't remember, I don't get what we're talking about on this slide. Because often I'm out doing whatever and I just jump on there and go, this is all I wanted you to know on this slide. Quit thinking about it. Nobody really here has emailed me too much yet. But that's available all weekend long. All the way up till Sunday night at probably midnight when I go to bed. I'm going to check and I look. Okay? So if you really don't know why we have a slide, because if you, what's the iPad, you know, I need a word for this. How do we know that something's going to be on the test? It's the part that you ignored because you didn't know what it meant. If you ignore something, it'll be on, if you email me, it probably won't be on anybody's test. But and I've already written the test by now, right? But you see what I mean? That's the catch. You don't know a word, you don't ask what it is, it always winds up on the test. I don't know why. So ask me. I'm available 24/7. Unless I'm asleep, I will answer. All right, I'll see you on Monday.